Hello, hello, hello. This is Will. Today is Sunday, February 16th, 2025. Welcome to From Bronze to GM and miniKanren, episode 9. So, our previous ladder practice, we had some micro, and then I'll call this micro and macro. Our micro was to practice consing up various tree patterns or nested list patterns, and then using car and cutter to access values in the consed up tree, and drawing box and pointer diagrams for those structures and predicting which printed representations of a cons expression will look like. And in particular, things like where will the parentheses be, and will you see any dots? All that. Okay, so that was the ladder practice. I hope you've been working on that. And then the macro was to write down ideas and observations. Remember, you've got your research notebook, either on paper or on electronic device, however, computer. And what you're reading, what you want to read, questions, potential research projects, all those things, okay? And that's something, I want you to keep up. Okay, so this is something we just keep doing as researchers. Keep thinking of ideas, keep writing things down, keep reading. All that never stops. That's like you never stop macroing if you're playing, that's, it has to become automatic. Okay. All right. So I want to talk a little more today about fundamentals. So the micro practice is about fundamentals for dealing with pair structures and improper and proper lists and car and cutter and all that stuff. And the macro practice is a type of fundamental as well. But what does it mean to be able to do something? Okay, so let's just take an example of consing up tree structures. Okay, there are at least two ways you can think about being able to do something. One is under optimal conditions, you can do it some of the time. Okay, so if everything is calm and you have time and you can be patient, you think really hard, then you can do it, at least some version of it, maybe a simple version of it. Okay, so sure, that means you can do it. But there's another version of it, which is you're tired, you're hungry, you're distracted, and you have to do something quickly. You're working on some problem that's very tricky at the edge of your ability, and you have to do something like cons up a list structure or a tree structure as part of that much more complicated thing, okay? And you have to do it quickly, right? Can you do it then? And can you do it with, 98% or 99% accuracy? Like, can you do it quickly and reliably? And if you do make a mistake, which should be very rare, can you immediately, figure out what's going on and fix it? There are things in Scheme like just dealing with the parentheses, right? So, all right. So here I'm in text mode for Emacs. So if I type left parens, I have to type right parens separately. Now I do have the matching in terms of the highlighting. Okay. But if I switch to my Scheme mode, Okay, so now we're in scheme mode. And so if you'll notice, if I type a left paren, I automatically get a right paren. If I go over here and I start hitting delete, nothing happens. Okay, now something starts to happen. Okay, now I delete. And so, and my editor is set up, you know, in a sort of a parenthesized mode. I can do things like go forward in S expression, go backward in S expression. I can transpose two S expressions. Okay, I can do all those sorts of things. Yeah, I can grab an S expression, and paste in an S expression. Okay, everything is set up so that when I'm editing, I'm doing like a series of transformations. It's like I'm dealing at the S expression level as opposed to dealing with strings or just like raw text. Okay, so I'm dealing with things as units. Okay. Okay, so I'm dealing with units instead of, you know, trying to type things in. If I can copy something or move things around, transpose things, I'll do so instead of typing, because every time I type, I make a mistake potentially. Okay. I don't want to have to type right parens. I want parens automatically to be balanced. All of those things are set up so that if I spend, you know, an extended period of time, which sometimes I do, you know, many hours, like hacking Scheme or miniKanren, like sometimes I'll spend, you know, basically all day doing it, or maybe even all night. I don't ever want to make a parenthesis mistake. I don't ever want to, you know, make these like low level mistakes if I don't have to. Okay, I'm not great at typing, as you've probably figured out. And yet I can still do, you know, Scheme programming and very rarely make that level of mistake. It's not like I'll never do it. It's pretty rare. So, you know, if I'm hacking Scheme or miniKanren, you know, the number of paren mistakes I'll make might be, maybe I'll make one parenthesis mistake every 2 hours if I'm, you know, programming like the whole time. Maybe I'll go more than 2 hours before making a mistake. Like my mean time between parenthesis mistakes is very, very long in terms of like programming. You know, I probably wouldn't go a full day of programming without making some parenthesis mistake, but it would be like very rare. Okay. Yeah. And when I was teaching Scheme, I would be writing on the board, either the blackboard or whiteboard or whatever. And I'd see students raise their hands like, oh, Dr. Bird or whatever, Will, I think you have a parenthesis mistake here. I think your parens aren't balanced. And I'd be like, no, they're okay. And the reason is when I'm writing the parens on the board, I'm matching them. And I would use my fingers to match them. I had all sorts of ways. And I don't think a student ever caught me in all those years making a parenthesis mistake. I mean, there are a lot of students who thought I made a mistake, but I had developed a set of practices to try to eliminate that as much as possible. So that's the other type of being able to do something. Okay. And I remember Day 9 talking about this from StarCraft. He said that he knew someone, I think a friend, who would, to prepare for tournaments, would practice playing StarCraft, with one shoe on and one shoe off, and their chair at the wrong level, and like the monitor, at the wrong height, and maybe with glare in the monitor. Practice while hungry, practice while tired, all those things, so that when they actually went to a tournament, they wouldn't be thrown off by the fact they're in a new environment. Okay. I thought that was an interesting idea. So that was this idea that Well, okay, you need to be able to do this under non-optimal conditions, right? You need to be able to do it quickly. You need to be able to do it accurately. Yeah, so those are just like fundamentals that they'll save you if you can rely on them. All right. And scheme's an interesting language because the core parts of scheme are actually very small. It's got a very small core, and there's something fundamental about it. It's based on call by value lambda calculus, which we'll get into. But the point is, it's a small language, and as Jerry Sussman likes to say, he likes to have a language that he can keep in his head without having to look up, things in a manual, right? I'm the same way. I want a language that's small, but Scheme gives you ways to extend the language, to redefine things in the language. You can redefine almost everything in Scheme. Some versions of Scheme, you pretty much can redefine everything. And then there are things like macros, where you can change the syntax, you can extend the syntax. Scheme has lambda, which allows you to define anonymous procedures. You can change what lambda does, okay? You can change the syntax, or you can change the behavior of lambda. You can change, all sorts of stuff. So it's a very flexible language and allows you to build up abstractions from a small core. So that's one of the cool things about it, is that if you really understand the core fundamentals, you can build up your own abstractions, which means, even if there is a library that's available, you don't necessarily have to use it. You can build up your own abstractions if you understand the concept. Okay, so Scheme's a good language, I think. If you understand the concept of something, then you can implement it. You can implement it the way you want. And if Scheme's not working the way you want, you can change it. Okay, so Scheme's a language, I think, that rewards having really strong fundamentals. Python, I think the way a lot of people use Python, I think it's somewhat different. I think Python is a language used by a lot of people as sort of a glue language, where you have a whole bunch of libraries, and you're sort of gluing together calls to the libraries, and maybe for like machine learning or something, the libraries are written in, say, C++ or whatever, because Python's not efficient enough to do those. And so Python's more of a glue language, and all of the interesting parts are actually in the libraries. The Python code itself isn't very interesting. It's like a bunch of procedure calls or method calls or whatever. So that's a different approach, and there are some advantages of that, and that's great for like code reuse and things like that. And that's an area where Lisp programmers have been dinged by sort of like the Lisp curse, or the fact that every Lisp programmer thinks they're the greatest programmer ever, and will tend to reinvent things. Okay, so there's some truth to that. However, at the same time, I like the fact that there's this core part of Scheme that's very simple, and you have then mechanisms to extend the language and give yourself abstractions. And just if you understand those parts well, you actually have extremely powerful language that's very concise, and that can allow you to do all sorts of things. Like if you look at, say, miniKanren, most of miniKanren, certainly all of microKanren, this is using very simple parts of Scheme, very simple features of Scheme, just combining those in an interesting way, and using some macros, using some function definitions, but macros are useful for having nice syntax. Okay, in the case of Scheme, in the case of miniKanren. But the point is, like the parts of Scheme you need to use to have miniKanren as a DSL are actually very, very limited. Now, if you look at faster miniKanren, that has some fancier things in it, but the point still stands that you can get very, very far in Scheme with just sort of the fundamentals, right? And that reminds me of the, like the pylons and probes from day 9, from his tutorial Tuesdays or whatever. Like, okay, just focus on these fundamentals, make pylons, make probes, don't get supply blocked, make workers. I was watching Vibe, one of his bronze to GMs today, and he was, spread creep, spend your larva, make workers, expand, make sure you're not supply blocked, make an overlord, hit your injects. And, he's doing this, while, talking and taking his hands off the keyboard, explaining concepts, talking in the chat and everything. The next thing you know, he's spread creep across the entire map to his opponent's, natural expansion. It's like, wow, okay. And he was just doing this macro cycle over and over and over again. And even though he wasn't trying to do it fast because he was still, showing bronze level ideas, he could execute on that, very easily. But on the other hand, it's hard. It's hard to have the fundamentals really down. Okay. But if you do have the fundamentals really down, then you can go really far. So that's something I really like about Scheme. And that's why I've been emphasizing things like being able to cons up pair structures, okay, and using car and coulter and quote and all those sorts of things, and being able to go back between different forms and, understanding what the dot means and be able to do box and pointer, all that stuff. Those are fundamentals. And if you want to read a Scheme paper from the 1980s or whatever, you're going to need to know, what a pair is. You're going to need to know what a dot looks like, what a dot is in an output from like the REPL or something. You have to internalize that at the level where, you're able to do things with pairs and quote and car and coulter and cons at the level of like not making mistakes for long periods of time. Like, if you were to program for 4 hours, can you avoid, making cons and car and coulter mistakes and quote mistakes? Like how many of those do you make? And I've worked with people who are new to Scheme programming, but who programmed before, and they could do it kind of, but they could do those things in the same sense that I was talking about before, where it's like under optimal situations, they could get something to work, might take them 4 or 5 attempts, but they could eventually get it. But then when you start doing more complicated things, you're starting to write recursive procedures, and now you have a bunch of recursive procedures together. Those little mistakes, they start adding up. And so if you're making one of those mistakes with using like car and coulter and quote or parentheses mistakes or whatever, if you're making one of those mistakes like every minute or two, you're never going to get anywhere. Once you have a complicated program, you're going to spend all your time debugging it, and you'll probably just give up in frustration. So you just want to get to the point. It'd be like constantly being supply blocked in StarCraft. Okay, you just have to get past that point. So anyway, that's what I mean when you can do it. Can you cons up a pair structure? Can you cons it up as quickly as you can type and not make any mistakes, right? That should be your goal, is that you can do it. You can do, and like all these things I'm showing you, if you can do them as quickly as you can type for the purely mechanical things. Now it's different from like language design. Okay. You shouldn't design your language as quickly as you can type in the keyboard. That's not the point. But for something purely mechanical, it's sort of like 5SD or 4SD for making drones, right? Like that should be something that is in your, kinesthetic, memory or whatever, where, that just make drones, overlord, make drones. You don't want to have to sit there thinking, okay, now what's the hotkey again? Yeah, you'll just not be able to macro properly. So anyway, pylons and probes. I played a couple years ago. I played a StarCraft 2 game, and I just got wrecked. I got wrecked. Like, it showed up in the first battle, and my opponent had like 3 times the army. And it's like, I thought I was doing pretty well that game. I thought it was macroing. And I started talking to the person. It's like, yeah, I'm a Korean semi-pro. Thought about going pro. And I watched, this person was obviously smurfing. I watched the replay, and it's like, okay, every single thing was smooth, right? So time to throw down a spawning pool. Well, the drone got to where the spawning pool would be just as you're hitting 200 minerals, and then instantly make the spawning pool, right? Everything was like that. The drone reached wherever the building was going to be just as the resources necessary. And so just shaving off those little things and the stuff that I was fumbling around, this person could do very, very smoothly. So it's still the same thing I was doing, just refined and, not making mistake, not getting supply blocked, right? Making the overlords on time, spreading the creep, all that. So same here. Okay. So with a language like Scheme, the fundamentals are really, really important. I don't know about, Jupyter notebooks and you're chaining together a bunch of calls or tying together a bunch of library calls. I think that's a different style of programming. But for the things we're going to talk about, the fundamentals are really important. Okay. And we're going to talk about like core parts of Scheme that we have to really understand. Like, we need to understand the semantics of Lambda. We need to understand evaluation orders for procedure application, all that stuff. We just need to know it inside and out. And we're going to implement things that will help us understand better. But, the fundamentals is just like pylons and probes, okay? Okay, so speaking of fundamentals, so I was already showing you this to some extent, but let's just make sure I am in Scheme mode now. So what I have set up, and I've already mentioned that what I have is a custom Emacs setup that I got when I was at Indiana University. Part of it, I guess, part of these files had been floating around Indiana for a while, and also Aziz Gulom helped me set up some things. Probably the closest, standard Emacs setup would be like paredit. So what I have is kind of like a stripped down paredit. I've tried using paredit a few times. Paredit has more commands than I'm used to. It has some nice commands, but I guess I'm just so used to this. And once again, like I like very simple things. Okay, ATCs instead of grigris. Just keep your hand on the keep your brake hand on the rope. Okay, it doesn't matter if you're using a grigri or ATC. You still have to have that fundamental. So I like very simple things. So I have, if I type a left paren, the right paren automatically appears. Okay. If you want to delete a paren, well, you can delete things when you have a pair that's like the empty list, then just delete with the point over, and I'll delete both parens. If I have things inside of the those parens, I can't delete. And it says can't touch this down below. It's like MC Hammer, can't touch this. Okay, so I can't delete. I can't delete that left paren. And if I try deleting right parens, it just sort of skips over. So I have to delete the entire contents first. Now I can always grab this thing, so I could do meta control K to grab the S expression and control Y to yank or paste it back. Meta control K on my keyboard is also escape control K, or whoops. No, that's not it. Yeah, so for this one, I'm using escape control K. I also have an external keyboard. Right now I'm using my laptop keyboard. Yeah. Now sometimes when you're editing things, you'll get in weird situations. Okay. So like you'll end up with like a paren by itself. You can see by that sort of purplish highlighting that this is a paren that doesn't match anything. Okay, so Emacs is not happy with that. And if I try to delete, nothing happens. It just brings it up to the next line. Okay, so I can't delete it by itself because I can only delete pairs of parens. So in this case, I can select the whole thing and then just like delete that one part, like I was deleting some text. So there's a way to get out of things. If, like I can delete just that part, and now I once again have an unbalanced paren. Okay. And I can just select it and delete it. So if I have to, or if I load a file, that has unbalanced parentheses, I can delete those. But in general, I'm trying not to. And so other commands are forward S expression, which is meta control F, backwards S expression, which is meta control B. Okay. And then there's also transpose S expressions, which is meta control T. So I put point in between the S expressions and it swaps them. Okay. And I can also do that inside like that. No problem. Yeah. So meta control K will kill an S expression, and then control Y yanks it back. Okay. So those, and also useful to know, control J inserts a new line. And then this is a really useful one. Okay, so see if I can remember this. My muscle memory remembers. If I'm actually trying to think about it, I have trouble. Nope, that's not it. Hold on a second. Sorry. All right. This is one of the things where if I don't think about it, I can do it no problem. But as soon as I start thinking about it, I'm like, what is this? How do you do it? No, that's not it. No. I'm going to forget this. So there's a command where you can like bring this up a line, which is a really useful thing. And I am just blanking on it right now. Like I said, this is like muscle memory. Well, let me try one more second, and I'm going to give up, and I'll show you another time. Yeah, I remember that this happened to my phone once. That I was just like so used to typing in my password, and one time I was like, okay, what's my password again? And then I realized like I had no idea what it was. I had to type it. My fingers knew. I couldn't write it down, and then as soon as I started thinking about it, I lost the ability to do it. All right. Nope. Yep. Sorry about that one. I totally forget how you do it. Yeah. Okay. Isn't that funny how the human brain works? I thought, okay, if I'm going to remember it, I'll remember it at the REPL, because there you have to use it. So if I'm at the REPL, if I'm at ShaScheme REPL inside of Emacs, then if I want to insert a new line, I can't just like, hit return, right? So if I hit return, it'll actually, send the whole expression to ShaScheme. Okay. Well, that's not what I want to do. Let's say I want to add a new line. Well, then I do Control J. Okay. So that's not entering the expression. So if I hit enter, then sure. So now let's say I want to bring the C back up here. Well, what I could just do this. I could just like delete it. Well, that takes forever. But instead, See if I remember. Yeah, yeah. All right, so can I do here? Oh, no. Yeah, okay. So it's shift on my Mac keyboard, shift option 6. So shift 6 is like the caret character, like that character. Okay. So I'm doing shift option 6, and that brings me up a line. Okay. That's really useful. So it's really useful to know Control J is a new line, and then shift option 6 brings me up. Okay, so that's very handy when doing REPL stuff. I use that for demos all the time. I couldn't tell you, obviously, what those commands were, but my fingers know. Yeah. All right. So those are basically it. Those are about the only commands I use. Let's see. There's one other one I've occasionally done. Let's see. See if this works. I'm not sure if this is going to work with my new Emacs setup. All right, so here I'm building, like a little add function. It's called add. All right. Scheme, toggle lambda syntax, Control C, Control Q, L. Let's see if I can do it. Yeah, okay. Control C, Control Q, L. So there are actually two types of syntax in Scheme for defining procedures. There's what I'll call MIT syntax or SICP syntax, which looks like this. So here we're using define. So we've already talked about define gives a name to a value. Here we're defining a procedure. Procedure would be called add, and it takes two arguments, n and m, and then the body of the procedure calls the plus to add n and m. Okay, so we have these two formal parameters, and we add them, add the values of those arguments, the arguments coming in. So I could call add 3-4, for example, and let me just make sure that works, right? So, okay, so option W takes a highlighted region. That's just like the regular Emacs command. So I'm not saying the standard commands. Okay, there you go. Get 7. Actually, there is one other command that's useful that I didn't mention. Control X, Control E sends the expression before a point. So point's the name of the cursor in Emacs. It evaluates that expression in the REPL. Okay, so if I want to, instead of like copying and pasting, I can just do Control X, Control E. Do you see how the caret down there? We got a new caret. I'll do it again. Control X, Control E, Control X, Control E. So basically the define is being sent. That definition is being sent to the REPL, and also Control X, Control E, that the add 3-4 is sent to the REPL, and we can see there's a 7. Now, what's being sent to the REPL is the expression or the definition or whatever statement that's immediately before the point. So if I do it here, Control X, Control E, 3 gets sent. So the expression 3 is sent to Scheme, Shea Scheme, and evaluated. Okay, so that's also a useful thing. Some people will, when giving like a demo or something, will use this approach. Personally, I find that's not the greatest thing for communicating with people, because if the person giving the demo is moving quickly, it's kind of hard to see what they've evaluated. And also, like you'll notice for the define, the only thing it changes is you get that extra caret, right? So if there are like a whole bunch of definitions and things like that, and someone's going through, you can't tell, you can't tell easily, are they sending every definition to the REPL, or are they evaluating every statement or whatever? So for that reason, and also if you see a transcript, then you can't tell what was happening, right? You can't actually tell. If you save this file, which I've been saving as a .scm file, you can't see what's going on because, okay, a caret, you see an extra caret. So that means, some sort of definition, let's say, was evaluated. Well, you don't know what the definition was. You can't tell it. Whereas here, if I just type in define, okay, now we know, right? So personally, I don't like that for demos, but anyway, it's a useful command to know. Control X, Control E. And it's also important to understand it sends the S expression, or the S expression in front of point is what gets sent. Okay. So anyway, I was talking about toggling. So there's a shorthand notation, which you'll see in the book SICP, Structure and Interpretation of Computer Programs by Abelson and Sussman, which looks like this. So this syntax for define is saying this, so it's really define. Okay, so define with this syntax is saying, okay, we're defining a new procedure called add that takes these two arguments, and then here's the body showing defining the behavior of the procedure. So that's one way you can write it. There's an alternative syntax, which I'll call the Indiana syntax, or the Dan Friedman syntax. Dan wants students to see define. He wants them to see lambda separately to understand what lambda is about. So we can toggle, which is Control C, Control QL, toggles back and forth. And we can see the expanded version. So these two are equivalent. Okay, so this top one is shorthand for this syntax. So I'll call this MIT syntax. Or MIT/SICP syntax. And I'll call this IU/Dan syntax. Okay. They're equivalent, but there is a command for the scheme mode to toggle between them. And then you can do, there's some other things here. There's also like meta x comment hyphen region. Okay, that's nothing special. Meta x uncomment hyphen region. So you can do that. In scheme, you can also do things like the hash pipe hash to comment out a region, or you can do, for an S expression, hash semicolon comments out the entire S expression. Okay, so there are different ways to do it. So, doing the line by line, comment region, uncomment region, not so critical most of the time. I don't use it that much. And let's see, is there anything else here? Yeah, I don't think so. Yeah, that's about, this is scheme quack. You can set quack things, run scheme or whatever. So I have it set up. So if I do, let's see if I get this right. Yeah. Control Z, Control C starts up Shea scheme. Now I can kill that buffer. Now if I do Control Z, Control V, it starts up Racket. Okay, so I go back and forth between Shea scheme and Racket for various things. The subset of Schemely stuff I use tends to run the same in Scheme and Racket, but for things like miniKanren, that's all written in Racket. So I have hotkeys, if you will, set up for both Scheme and Racket, and I can go between them. Yeah. So, but that's my Shea. Okay. That's my Shea scheme. Yeah, so those are basic scheme editing commands. Now, if you want, I can, post my Emacs setup files to GitHub, they're not the cleanest. Okay, and in fact, I've got all these directories and stuff full of junk, and I'm not sure how easy it would be for me to pull everything apart just for Scheme. Maybe I could do it. So I'm not really recommending anyone else use this. Okay, like if you were starting out, maybe if you want to use Emacs, maybe ParEdit would be a good place to start. If you want to use the same thing I'm using, just let me know and I'll upload it. For Lisp, historically, and for Scheme in particular, historically people have tended to use either Emacs or Vim or /VI. I guess maybe because the academic bent or whatever. And of course, Emacs has a long history with MIT. But Emacs has good support for Scheme, and there's Emacs Lisp, which isn't Scheme. It's definitely different. But the fact that you already have an editor that has a Scheme-like language, a type of Lisp as an extension language, it's got pretty good. So Emacs has pretty good support. The way people edit with Vim is quite different. So, I'm not a Vim expert. I'm always, it's like, okay, how do I get out of Vim? See if I can remember that part. So the hardest part of using Vim is getting out of it. So I don't, I'm not really qualified to say how you edit things, but I do know people who are expert schemers, all of whom started with Emacs, and then for one reason or another, they ended up running on a machine that was so slow or under emulation or something like that, where Emacs was too slow and too memory hoggy to run. So in those cases, they switched to VI or Vim. Certainly Vim or VI is more lightweight than Emacs, although for modern computers these days, Emacs seems like pretty skinny in terms of how big it is. So I just don't know. I just do know that people edit VI and Vim using VI and Vim differently. They tend to edit it very differently than they do in Emacs. Okay, so and there are fancy modes you can get. There's ParEdit. There's another one called ParInfer, and that one, when I was reading about it, that one scared me a little bit just because it seems like it tries to guess what you're doing. It seems like, well, I guess that's kind of what these LLM things do, right? It's trying to guess what you're going to do. So I don't know. I haven't used that one either. But, I try, I like simple things. Okay. So I, my editing stuff I have is pretty close to what I want. Maybe there's something called, was it slurp and barf are two commands that you get with ParEdit. Those I think would be helpful. So I've thought about trying to add that, but so far at least I haven't done it. So anyway, those are the sorts of commands that would be helpful. But on the other hand, like I said, once you get used to things like paren matching, and so for paren matching, by the way, if you're working on paper or if you have an editor that doesn't have support for like the matching, like most editors will do this at least, like they'll visually show you if parens are matched. Okay. But say you're working on a whiteboard or a blackboard or paper or something like that, or in an editor mode that doesn't have anything like that, or someone's projecting code and you're trying to match things. One approach is just to use your fingers. Use like a pointer finger from your left hand for the left parens and pointer finger from your right hand for the right parens, and just make sure that they match. Okay. So literally move your fingers in and another thing, like a basic check is that there better be the same number of left parens as there are right parens. So let's count them. So left paren, left paren, left paren, left paren, left paren. Okay, so that's 5 left parens. And a right paren, right paren, right paren, right paren, right paren. So there are 5 lefts and 5 rights. Now, that doesn't mean they're balanced, but if the numbers are different, I could tell you they're not balanced, okay? I could tell you for sure they're not balanced if the numbers don't match. So that's a basic thing, but you could put your fingers like where, here's, put your finger here, put your finger here, on both sides, and start working your way in. So that's one thing you can do. And so that's how that's why when the students would say, I think your parens are not balanced, I was like, I'm pretty confident they are because I was doing that, but I think the students probably didn't catch that I was doing it. So I was pretty fast at it, and usually I could just like kind of eyeball because part of it is, the other thing is you want your editor set up so it knows something about indentation. Okay, so Okay, so if I do Control J, notice that it indents under the E. Let's do another let. Okay, and we can do things like there's a conditional operator called cond, and so we could write if x is 0. Return 0, else turn, I don't know. I'm just making something up, okay? Yeah, so we got some sort of indentation going on. They're more complicated syntaxes, okay? So, but notice here, else is a keyword, auxiliary keyword that matches cond, or that's part of like the cond syntax. So let, these are highlighted in different colors. 0 question mark is a procedure, built-in procedure, so is plus, and so is times. So notice that those are not in the blue color. Okay, so that's there are lots of things that you could play around with. Let's see. Trying to think if there's a nice example of something with complicated syntax. There's some stuff with pattern matching or whatever. I don't really want to get into that, but the point is when I'm hitting new line, or like, okay, so like I'll do a new line here for a new binding. Look where it shows me. So it knows that I'm still within the binding structure, right? So yeah, just basic things. Okay. I can do a Control J here. It knows where to put things, all that. If I look at my .emacs file, okay, actually that's a good place to look. .emacs, okay, so let's look. I've got a whole bunch of stuff about indentation. Yeah. Yeah, so I've taught Emacs about all sorts of things, mostly having to do with miniKanren and miniKanren variants and extensions. Well, the point is that there are different levels of indentation. So there's something called scheme indent function. So here you can see I'm requiring quack mode for Emacs, and then I can do this put, and then whatever it is, cons, list, fresh, whatever, scheme indent function, and then there's a number. So I've got 0, 1, 2. I don't know if those are my only things I'm doing, but so there are at least 3 different ways, 3 different styles of indenting. So yeah, I can teach Emacs about those. Okay, so that's a nice feature to have. Nowadays, there are fancy text editors using, was it the language, like LSP, language server protocol, and I think Emacs has a ability to do an LSP thing. There are people who use, the Microsoft Visual, what's it called? I have it here. I started learning it recently. Just playing around saying, Visual Studio Code, VS Code, and that's got, that seems to have versions like modes for every language. So, and I know for VS Code you can set it up to have Emacs bindings. Yeah, whatever. Set it up. Set up something that works for you. But these are the sorts of things that I find handy. Okay, like I said, it doesn't have to be super complicated, but you want to make sure you're not fumbling around. It's nice to have the indentation taken care of. It's nice to have the parens taken care of. But I personally like to keep it simple. All right. So I wanted to talk a little bit about, quotation, quote, and building up these list structures, cons, all that. So why do we care about this? Well, lists are generally useful things, okay? Lists can be sequences of instructions, for example. Also, all sorts of things you can do with lists or trees. Obviously, trees pop up all the time in computer science. But in Lisp, and certainly in scheme-style Lisp, there is a really important connection between the code for Lisp programs and these lists that we can cons up. Okay, so let's take a simple example. I want to add 3 and 4. Okay, so here is an expression that will add 3 and 4. I can evaluate it. Okay, so we've seen this before. Now, if I put a quote in front of that expression, what I get back is a list. Okay, this is a list of length 3. All right. Now, given our practice for the last few episodes, we know we can build up that list multiple ways. So instead of quoting the whole thing, we can do this. Okay, just call list on it, or because 3 and 4 are self-evaluating literals. If we wanted to, we could quote 3 and 4. That doesn't make any difference. And of course, we can use our friend cons. Okay, did you see the little dance I had to play to stick everything in the conses? That's what like the par and for slurp command lets you do that more elegantly. So that's the one type of command that would be nice to have, I think. But the rest of the par and so that's for par edit. The rest of the par edit stuff I don't particularly want. So but in any case, we muddled through it, and so we could see, so we can construct this list in different ways. But the bottom line is still, it's a list of length 3. And, we know about car. The car of that list is plus. and plus is a symbol. It is not a procedure. Okay, this is important. If I just type plus at the REPL, I get the procedure bound to plus. If I quote plus, I get the symbol plus. Okay, these are different things. Very important to understand this. Okay, so the variable plus is bound in the initial environment to a procedure that knows how to do addition. If I do quote plus, which we remember is the same as that, I get back a symbol. Okay, the symbol plus. Yeah, all right. So these are different. Now, there is a procedure built into Shea scheme or to scheme called eval. Okay, you can see it's a procedure. I can eval the quoted plus. Okay, remember quote plus evaluates to the symbol. And when I eval that, I get back the procedure. So remember REPL is the read eval print loop. Okay, remember the eval part? Well, there it is. That's the eval. So the eval can take data. You can take data representing expression like a list or a symbol or whatever, and then evaluate that. Okay, so we're going to write our own eval. We're going to write an interpreter or evaluator for scheme at some point. But just know that there's something already built in. And so that's what we're using when we call the REPL. Or like, I'm sorry, at the REPL, that's what's being called, is that there's an eval. Okay, so we could eval not just the symbol plus, but this entire list plus 3, 4. Okay, and that will give us 7. Remember, quote plus 3, 4 evaluates the list plus 3, 4, where plus is a symbol. Okay, so we have the ability to go from the REPL, where if we write an expression at the REPL, we get if we write plus 3, 4. Excuse me. That expression, that symbolic expression, is evaluated and evaluates to 7. If we quote it, quote of datum evaluates the datum. So quote of the list just gives us back the list. And so we have, this plus is a symbol. But if we eval that quoted list, we could do it another way, okay? Just to drive home what's going on. Okay, I'm going to define my list to be that quoted list. Okay, there's the list. Take the car of it. Okay, sure enough, that's a symbol. So we have my list, and if I eval my list, I get back 7. Okay, so this is very interesting that we can take an expression, this is code, right? And then just by quoting that expression, we've taken the code and we're now treating it like data. Okay, so now instead of evaluating the addition, we just get back the list that represents that expression. Okay, so this is what is sometimes called code data isomorphism. There's also a term homoiconicity that you might hear, Now, what exactly that means, I think is debatable. So I'm not going to go into that, but this code data, actually with any of these terms, I think often when people use them, they're not really clearly defining them. We're not going to get into that. You just may hear these terms, that wording from people. The point is, I can take an expression that if I just evaluated it would produce, some value, or maybe it goes in an infinite loop or gives me an error or something. Instead, I could just quote it. So, remember we saw before, if I divide 5 by 0, that's an exception, get an exception, but I can quote that expression and I just get back the list. All right. So I'm not evaluating the expression. I'm not doing the division. When I put the quote in front, I just quote of datum is datum, get back the list. Okay. Now, so one of the interesting things then is that because we have a list, right, and we have symbol here, we can just do our list operation. So we know we have cons, we have car, we have cooter, we can quote the empty list, we can ask null question mark, we can ask list question mark, we can ask length, we have all these sorts of things, okay? So if I wanted to, I could do something like this. So I could say, okay, here's our list. Let me just give it a name. Let's call it L. All right. Actually, just to drive the point home even more, let's build L by consing up. Notice how I don't type anything when I can avoid it. I just grab the expression. All right. So here's L. That's our list, right? Length of L. We can ask if it's a list question mark. Yes. Is it a pair? Yes. It's a list and it's not the empty list. Okay. So all those things. Great. Now, what's the car of the list? Well, the car of the list, of course, is the symbol slash, or however you want to call it. And what's the rest of that? What's the rest of L? Well, the rest of the L is the list 5, 0. Okay, so those are the arguments that we're going to be passed into slash, basically, or to divide. So now what could I do? Well, how about this? We don't want to have a mishap with division, dividing by 0. So how about we do this? Let's cons the symbol. Okay, we're getting this by symbol. The asterisk symbol, because we're quoting it, okay, onto the rest of L. And now we get a new list. Okay, so we've replaced the slash with the asterisk. And now I can evaluate that list. And sure enough, we get 0 in this case because 5 times 0 is 5. So, well, let's see. What else could we do that would be interesting? Oh, okay. I know another thing we could do. All right. So instead of replacing one arithmetic operator with another, I could replace the operator. I could say cons. Okay. So now we have cons 5, 0 is the list we get back. Okay. And I can eval that. What do we get back? Okay. You should be able to predict. Okay. Let's practice our prediction. What do we get back when we cons 5, 0? The pair, the dotted pair, 5.0. Okay. Great. So Here we've played some games. We've done a style of metaprogramming where we had an expression, right? So we had L. I mean, originally we had something like that. Maybe we read this in from a file or something, okay? Or maybe over the network. So we have this expression. We could choose to evaluate it right away, okay? Or if we decide that we're going to quote that, and then we can treat this expression as data. We can tear it apart, inspect it. We can build up a new expression that reuses the arguments in various ways, whatever we want to do. And we can, construct a new expression based on this and then evaluate that expression. Okay, so it's a type of metaprogramming. Programming, programs or programs about programs. I remember one thing that Kent Divig said when I was sitting in on one of his classes. This may have been the honors intro class at IU. I may have been talking to undergrads, but he said this very interesting thing, which was that most computer programs are written by other computer programs. Nowadays with LLMs, maybe that's not so surprising, but his point was, like a PDF document is a computer program. A PostScript document is a computer program. There's a zillion of those sorts of things. Every time you print something on a laser printer, you have a computer program that's generating a computer program to be sent to, the printer. So stuff like that. So it's metaprogramming all around us. Scheme's an extremely powerful, flexible language for metaprogramming. So what I'm showing you is just one type of metaprogramming. There are these hygienic scheme macros. Also, there's, fancy ways you can combine things with scheme macros and records to build really sophisticated metaprogramming systems for writing compilers. You can look at the work that, like Andy Keep's dissertation work. He's given a number of talks on that. That's really interesting stuff. So Shea Scheme is built using this NanoPass framework. So that's a very sophisticated metaprogramming system. What actually involves multiple types of metaprogramming. Racket is like a super metaprogramming system with, towers of languages built with a very, very fancy macro system. So anyway, this is just a very small example of how, we can start playing these games. And the games are very convenient because the syntax for the code, it's like basically we have lists representing code, right? These S expressions. And as soon as we have quote and things like that, we can, move things around, tear lists apart. We can also do pattern matching and recursion. We'll see all those things in a bit. But in any case, that's one reason why understanding how lists work and what a symbol is and how quote works, all those sorts of things is really important. Okay, so this is sort of bread and butter. And so you might have macros, you might have recursive functions, or recursive relations when you get to miniKanren, but still, underneath the hood, they're like pairs. Okay, and this also has to do with the memory usage, and if you want to study time and space complexity and all those other things, you need to know that that there are things in memory that are being created. You need to know about the heap and the stack and registers and all that if you really want to implement a scheme, say compiler and runtime system. At that level, you need to understand those sorts of things. We're going to ignore all that right now, but the point is with lists, the ability to treat these lists as code and to manipulate lists, and the ability to quote expressions, very, very powerful. Okay. Really, really powerful. and it's a type of metaprogramming. Certainly there are other types of metaprogramming you can do in Scheme. Now, we've seen quote. Okay, so that's this character. It's like the upright character. There's another type of quote in Scheme. Actually, there are a couple types of quote, but the other main type of quote for lists, there's another type of quote having to do with like macros and syntax. Okay, I'm not going to talk about that, but for lists, there are two types of quotes we're going to use. There's the upright quote, and then there's this back quote. Okay. Now the back quote on at least the US keyboard, it's the same key as the tilde key in the upper left, like right above tab and below escape. It's that key right there. Okay. And look how they're different. Okay. Now, unfortunately, the way LaTeX with computer modern font typesets these, they're both curly, and you kind of have to squint to tell them apart, which I find really annoying. So just be aware of that. If you're reading a document typeset in LaTeX with like computer modern font or whatever, you'll see that instead of being the upright, it's like that's curly, and then the back quote's also curly. Now, if we remember correctly, we remember that this quote symbol for say cat, well, that's the same as writing left paren QUOTE cat. Okay, so this is like sort of like the fully expanded way to write it, and then this is like a shorthand. So in Scheme we don't have a lot of shorthands, but this is one of them. Okay, this just gets to be awkward to write, so like that upright quote is convenient. The this back quote thingy. Well, let's take this. Okay, so all right, so if we wanted to quote that list, we just put a quote in front of the whole thing, right? No problem. So that's the same as quote over the whole list. No problem. But there's another type of quote. So the back quote is quasiquote. Okay. So that's this back tick or back quote. Okay. The full name for that is quasiquote. Don't be surprised if you hear people call it back quote or back tick. Okay. That's a lot of people will say that, but or some people will just say quasi. Quasiquote is just kind of long to say, but this is, you should know that that's what shorthand. Okay, so this backward, this backtick thing, it's actually quasiquote in the same way that the upright quote is QUOTE, and then there's extra pair of parens. Okay, that's the first thing to know. The second thing to know is, well, look, it seemed to do the same thing. The quasiquote seemed to do the same thing as the quote for that list. So what's the difference? And in fact, I can quasiquote cat to get the symbol cat. I can quasiquote 5 to get 5 back, because 5 self-evaluating literal. So far it looks like quasiquote and quote are identical. Like, so why do you use quasiquote? The reason is sometimes you have lists that where when you're programming, most of the contents of the list, but then there's some unknown part that you want to fill in with a value of like from a variable or whatever. So the example that Dan gives, which I think is a very nice one, is like this. Okay. Now quote that whole list. Mary had a little lamb. Well, what if we want to replace little. Okay, so maybe we still want this list, but we want to be able to change little. Maybe we want a variable, or somehow we want to pull out the little and be able to replace into it. Well, so we could do something like have a let. And we could say, okay, we're going to have a size. So the variable size, we're going to have a variable binding size, and it'll be to the symbol little. And now what we're going to do is we're going to use our quasiquote. And then instead of little, we'll replace that with this thing called unquote, around size, or before size, I should say. Okay, so the unquote, or a comma, is escaping out of this quasiquote environment. So it's sort of like a string interpolation, if you've seen something like that. So the idea is that with this quasi-quoted expression is for almost constant data. That's the term you might hear, almost constant data, where, if the entire list was constant, we just use a regular quote. But here we want to be able to evaluate an expression. Okay, so what's happening is, well, Mary is like a quoted symbol, had is a quoted symbol, A is going to be a quoted symbol, lamb is a quoted symbol. But size, because it's unquoted, well, this expression will be treated, will just be evaluated as if it weren't in this quasi-quoted environment. It'd be just like we had, just as if we had written size inside the let. And so what will happen is size will be evaluated. This is a variable reference, and the value bound to size in the let will be the symbol little, and then sure enough, here we have this list that's constructed. Mary had a little lamb. Okay, so there are a few parts to this. So first of all, okay, so just like the quote symbol stands for QUOTE, wrapped around the thing in parens, and quasi-quote, the back quote is like quasi-quote wrapped around in parens. The same with comma. Comma is unquote wrapped around the thing in parens, okay? So that's the full syntax. And if we really wanted to be explicit, okay, we could wrap quasi-quote around the list. Now I think you're seeing why the shorthand exists, because this is pretty annoying to write. So I'll go back to the concise version. Okay. Another thing to say about this is, the quasi-quote and unquote, they're not actually needed in the sense that this is like a convenience. If I wanted to, I could construct the list like this. Okay, and that, so you can think of the quasi-quote. When I said the thing, the expression following the quasi-quote was not, constant data. That's the part that was like unquoted. That's what I mean. Okay, so, that's the part that's not almost, that's the part that's not constant. So I can replace my use of quasi-quote. I could just build up the whole thing with list, and then I just have to, explicitly quote all of these expressions that are not unquoted. Okay, so that's something worth knowing. Another thing is, I don't have to, just have a symbol here. So like I could say, I could do something like that, where I have a number. But more to the point, I could have some arbitrary expression that's getting evaluated. Okay, so going back to our list rewriting in terms of list, be like that. Okay. Of course, I can have more than one expression that's unquoted, right? So I can have more than one if I want. Yeah. Okay. Now, once again, like I showed you with eval and where we're playing games with plus and divide, often where you see this sort of thing is going to be with code. Okay, so what we might have, okay, so we have lambda. Oh, okay, see there? There's a paren problem, right? Do you see that? I was not careful. Yeah, I was not careful grabbing this. All right. Okay. I don't count that one as much of a paren problem because I caught it right away. Okay, so in Scheme, we often have expressions like here's a lambda expression, which will evaluate to an anonymous procedure, a procedure without a name that takes one argument, and then when given that argument, we'll add the argument to 3. Okay, so here's the procedure, and if I want to directly apply that procedure, I can wrap parens around it because parens mean procedure application unless the thing immediately after the left paren is a keyword like let or lambda or whatever. We'll go through those evaluation rules more. But in any case, here we go, we get 8. Now, if I wanted to, I could play the game that I was playing before with Mary Had a Little Lamb, like this, where I could say, okay, we have a body of the lambda. There we go. All right. And maybe we have another binding here. Let's... Okay, so I pulled out the formal parameter, x, and I pull out the body. And so it's the same thing as with Mary Had a Little Lamb. Okay, and when we get into interpreters, we're going to use this sort of pattern, this quasi-quoted or back-quoted pattern, where we have expressions like lambda or let or cond or if or any of these other things. And we're going to have, unquoted parts inside this quasi-quoted expression. And we're going to use this with pattern matching. Okay, so this quasi-quote and unquote, along with pattern matching, which we'll see in a bit, is very powerful and allows us to succinctly write code that keeps the shape of things, okay? Now, really what it would probably look like if we were writing a pattern might look like that, or this is probably more like what we would write. Okay, So we have lambda y plus y3, and I abstracted it and say, x is a pretty generic name for, formal parameter. So, and then E stands for expression. So that's what the body is for the lambda. So this is the sort of pattern you would also often see, quasiquote, left paren, lambda, left paren, comma x, left paren, unquote x or comma x, and then comma E. So we'll see this sort of thing a lot. Okay. So we'll have something like incoming an expression we want to pattern match against. And maybe this will be our pattern matching pattern. So we'll match this pattern against this input list or expression. And what will end up happening is that the x will be bound to y, and then the E will be bound to this list plus y3. It's sort of like a reverse of what we're doing here. Okay, so it'll like generate the let instead of we have a let that fills in this template. It'll be sort of like that, but it'd be like, let's dynamically generate the X and E bindings, and then we can use we can refer to X anytime we want to know what this thing is, or build up an expression using the formal parameter, and we can refer to E anytime we want to access this body. Okay, so the pattern matching is very convenient with the quasiquote and the unquote. So like I said, we could build this using list, but you saw it started getting kind of out of control. And so the nice thing is as the code becomes more complicated, it's nicer, becomes increasingly nice to be able to see the structure of the code when you're reading it. And that's something the quasiquote and unquote gives us. Okay, so very nice for pattern matching. We'll get to that. And then I'll show you one other feature, since I'm showing you quasiquote and unquote. I'll show you one more thing. And by the way, you can do things like, use quote inside of quote. You can use quote inside of quasiquote. You can use quasiquote instead of quote. You can do all sorts of things. You can do stuff like quasiquote, quote, quasiquote, quote, cat. And that evaluates the quote, quasiquote, quote, cat. You'll see stuff like this too. When you start getting into code generation and really complicated pattern matching, you can get into all sorts of kind of weird things. But just be aware that like you can have something like a quasi-quoted list that has a quasi-quote inside of it or has a quote in front side of it. This definitely comes up for real. Okay, so you can nest these things. They can involve unquotes, and also you could do stuff like you can write stuff like that. So you have a quasi-quoted expression that's immediately unquoted. So this would be like we had just, entered the expression plus 3, 4, and so the value is the 7. Okay, so there's stuff to know about this, in terms of just like practicing with quasi-quote and unquote. I'll show you one other thing called unquote-splicing, and then for your ladder practice, I'm going to have you look up quote, quasi-quote, unquote, unquote-splicing in the Scheme programming language 4th edition, and go through that and practice writing expressions down. Okay, so that'll be part of your ladder homework or your ladder practice. Okay, so let's go back to Mary had number lambs. Actually, we had the adjective before that, right? A size lamb. Okay. That's a nice one. Let's do this. So Mary has multiple animals now. Okay. Now notice how about this? We'll make it a little more interesting. Okay. All right. So Mary had animals and her lamb, and animals is the list: cows, fish, cats. Okay. So Mary had cows, fish, cats, and her lamb. Okay. So this is pretty convenient because maybe we've somehow built up a list of animals. Maybe we have a recursive function, or maybe in miniKanren we have a run query that generates a list of animals. And then we want to include that in the list of animals that Mary had. Well, the issue is, what if we don't want this extra set of parens? Okay, so what if we just want Mary had cows, fish, cats, and her lamb without the extra list there? Well, what we can do is do comma at. Okay, comma at. And you can see that this list has been spliced into, the contents of this nested list have been spliced into the outer list. Okay, so this is called unquote-splicing. I think it's hyphenated. Yeah, okay. Once again, not something that I would normally type a whole lot. It's just kind of awkward to have to write that a lot, but that's what you'll see. And I think some people call this like splat. I think that's right. I don't know. It's not used nearly as much as like unquote, but sometimes it is used. Okay, so you should know about it. Should know it exists. Okay, so now we have quote, quasi-quote, unquote, and unquote splicing. Very, very handy, especially when we get into pattern matching. It's going to be really important you understand how these things work, okay? Especially the quasi-quote, the unquote. The unquote splicing, yeah, sure, you need to know that exists and maybe play with a little bit. But the quasi-quote and the unquote, and then the regular quote, like those are going to be just like bread and butter. We're going to use them all the time, okay? Like all the time, especially with the pattern matching. You just have to have those down. And then the unquote splicing, that will come in. That will come in sometimes. I don't know. You probably, at least for the things I do, maybe 1% of the time, if that, you would use the unquote splicing. It definitely does come up. Okay, so you need to know what it is, and you should play with it some and all that. But it's just not used. It's just doesn't come up the same, to the same degree. Okay. Okay. And I'll show you one other thing. Okay, so Mary had comma at animals. All right. And we know that if instead of the comma at, we just have the comma, then we have the list spliced in, right? Well, if the list comes at the end of an improper list, okay, so now we have dot, Mary had dot animals. Well, look at that. It's spliced in. Okay, but we didn't have to use the comma at. It's just, remember we have a proper list. The definition of a proper list is either the empty list or a list whose last cooter is a proper, whose cooter is the proper list. Okay, sorry, pair whose cooter, I totally messed it up. A proper list is either the empty list or a pair whose cooter is a proper list. Okay, so remember you could expand this out. right? So, we have multiple pairs here. Now let's go ahead and expand it out, okay? Okay. Or if I wanted to, I could cons it. Okay, I could get rid of the quasi-quote and cons it up. Okay, I could do it that way as well. That's the sort of thing you need to be able to do. Okay, when it's talking about, like, you need to be able to do this stuff. Do you see how I was able to go back and forth and add the dots, right? And change it to cons, all that stuff. You need to be able to do that, okay? Like, you just have to do it. You just have to do it. It has to be accurate. It's not that much, okay? This is not getting the GM in StarCraft. Like, it doesn't require a lot of practice, but you have to be able to do it, okay? I don't know. Different people learn at different rates, and depending on how efficient your practice is, if you don't know how to do this already, maybe it takes you half an hour, maybe it takes you 2 hours. It's a small amount of time to get used to this and to be able to do it, okay? When we get to the pattern matching, you'll have more chances to practice it. But that's stuff you need to be able to do. I'll save this in the transcript. Great. Okay, so I wanted to go over quasiquote, unquote splicing and eval. And then for your macro practice, remember my definition of macro is, things like reading, thinking high level research. For the macro practice, I would like you to start looking at some classic AI systems, classic artificial intelligence systems or proposed systems that have some sort of connection to Lisp. Remember, Lisp was an AI language from the very beginning, sort of good old fashioned AI, GOFAI. And Scheme also has a long tradition of being used in AI systems. So this book, Software Development for Flexibility, SDF, that book is very much, flexible software techniques, from building in systems that exhibit intelligent behavior, that sort of thing, okay? So in any case, McCarthy's Advice Taker. This is like from 1958, 59-ish. You can find the paper on Advice Taker by McCarthy. Very interesting system. And he talks about how you might like it, how you might use it. Now, the interesting thing is, you could find the paper where he gave this talk. He presented about it. As far as I know, he never built this thing. I don't even know if he seriously tried to build it. But he talked about it in the late 50s, and at least one person in the audience was not having it. So it's very interesting. Sort of like the Hopple, at least the Hopple 1 and Hopple 2, you get to see the questions from the audience. I think that's very interesting to read those sorts of proceedings. So you can find, where he presents this advice taker and also the reaction. And there was someone in the audience who was like an NLP researcher who was like not having it at all. So I think that's interesting. Now, if you look at this paper for advice taker, I think the way I look at that paper is with a charitable interpretation. Okay, what was he trying to get at? I mean, remember, this is 1958, and he hadn't fully fleshed it out. But what was he hoping to be able to build? And so he has some examples about like going to the airport or whatever. I didn't find those like particularly compelling. I would try to get past maybe some of the flaws of that level and try to think, okay, well, what, McCarthy was a very brilliant person. What was he trying to get at? I think there was something there. Okay. And another question is, when you're reading this, is there something we could build today? Or, alternatively, do like modern LLMs? Is that, equivalent to advice taker? LLMs using tools, is that equivalent to advice taker? Or is there something missing or something different? I think there is something different still, because my understanding of his vision of advice taker was that, the system could sort of bootstrap itself in different areas by taking advice by people and getting more capable over time. While it is true that an LLM can interact with a person or some other agent to at least temporarily increase his capabilities and to use tools and all that, and now we're starting to play around with memory and so forth. I don't get the sense of if I interact with one of these LLMs for a long period of time, that it's like going to get really good and remember all that. And, that my investment in teaching it or giving it advice is going to pay off longer term. I feel like, okay, the next time next time it leaves the context window or whatever, it's going to run the trouble again, the same trouble. So that I think is somewhat different than advice taker. And also the focus on logic is different, I think. And then Doug Lennett, work on AM, Eurisko, and Psych. I think that's very interesting to look at the progression of those. When Lennett passed away a couple years ago now, his Stanford account became public, and there was source code for a version of Eurisko. I think not the final version of Eurisko, but a version of Eurisko, and I think for AM that people saw. And so now there's been a digital archaeology effort, and also there was a previous effort, I forget where, like Texas A&M or something, to try to do something like an AM. So anyway, I think it's worth reading about these systems, and there are a number of papers on it. So, and then Psych, which is, and there's also these things called discovery systems. Okay, so like AM, Eurisko, or discovery systems. Psych was like the big project that Lennett worked on for many years, and had, these systems had Lisp, certainly Lisp influence, extreme Lisp influence, and sometimes use Lisps. And also there's connections with logic programming, stuff like that. So very interesting systems worth reading up on. And it's interesting to see that people are now revisiting Eurisko and maybe AM. Also, these truth maintenance systems, and you could find the John Doyle paper, the original one on TMSs, and there's Building Problem Solvers. The book Building Problem Solvers talks about it. And then Propagators, Alexei Rudul and Jerry Sussman, you can find that sort of thing. So, these are all either in Lisp or highly influenced by Lisp, or, you can sort of feel the Lisp when you look at them. So I think that's interesting because, Lisp wasn't created in a vacuum. Scheme wasn't created in a vacuum. And there's this long history of a certain style of AI. And it's worth, I think, going back to the roots and trying to see what people have done with that. Yeah. So, that's your macro practice and, kind of your reading and research notebook and all that. Start, pick one of these, it doesn't matter what it is. Do a little bit at a time. Okay. Or you could just do a quick pass and, maybe read a little bit about each one and then decide which one looks most interesting to you to go back and practice more. Okay. So ladder of practice. So the macros, macros. read about. One or more of those systems, okay? That's your macro practice. And then for your ladder practice, for a micro, okay, so read up on quote, quasi-quote, unquote, and unquote splicing in the Scheme Programming Language 4th edition by Divig. And play around with these in the REPL until you can do it. Okay, or when I say in the REPL, you could also do it in a file and load the file, whatever. But the point is, you want to be able to use all these. And you could use them in the context of lists and all that, right? So quote, quasi-quote, unquote, and unquote splicing. Just make sure that you can kind of play around with it. And when I say do it, like I said before, my definition of do it isn't like if everything works perfectly and the stars align, you can get it to work. That's not what I mean. What I mean is you can do it in your sleep. Okay. Just like with the car and Kutter and Khan stuff. Okay, you need to be able to do this stuff in your sleep, just like pylons and probes. Okay. All right. There we go. That's plenty. Yeah. And if you want to, you can set up an editor also to get all that working. And if you want me to post my Bizarro Emacs setup, I'm happy to. Like I said, it's not like I would recommend that to anyone. If you're starting from scratch, maybe you want to try out ParEdit and see if that works, or maybe you got a totally different setup. Maybe you're not using Emacs. I don't know. I think ParEdit is available for multiple editors, I think. In case, you can play around with that as well. In any case, make sure you have some sort of editor set up where you can edit Lisp efficiently and not trip all over yourself with making mistakes. Okay, that's it for today. GLHF. Hope to talk to you soon. Bye-bye.